Hello. In the previous lectures, we were doing the case of unequal masses and what was the case? And the unequal masses and the springs with some hiccups and some difficulties. However, we ended up getting some solutions. Although the problem was not that well defined, so we did not have much access to initial conditions, and because of which we just found the general solution or generally the normal coordinates and normal modes associated. Now, in this particular lecture, we are going to start with something called as weak coupling, where we are going to play with the uh, spring, which is connecting these two masses. Okay, so here we are going to begin with something called as weak coupling. Okay, so now instead of unequal masses, I'm going to change the problem to changing the you can say uh, the spring constant. Okay, so that we're going to do. So let us study the case of weak coupling. एक थोड़ा सा सोचना. Still there are difficulties with the laptop. What will happen? Just give me a minute. So, okay. So this is the case of weak coupling and the phenomena of beats. Okay, and what is the problem statement like? So I'll define the problem. So let us consider two. Shucks. So let us consider the case of. So let us consider the case of two masses. Now we are going to take equal masses only, not to complicate the problem. So let us take two masses. The only difference that I'm going to do is that this particular spring is like say small k, has a spring constant small k, and this is, let's say, again mass capital small m only. And now instead of this k, I'm going to use some kappa here, and here you will have again k. Okay, so in this case, what we've done, the spring which is coupling both of them, so you can say uh, the spring which is coupling both of them has a differing, or you can say the middle spring has a differing spring constant denoted by kappa. Okay, denoted by kappa. And now let us for at least some sort of creating some sort of stability, some sort of you can say what should I say? For easing our problem, let us take some initial condition. Let us take some initial condition. So first of, there can be two conditions. One, I can impose my condition on the left mass, and another can be to impose condition on the right mass. However, the cases will be same. I mean, the answers would come out as same. Probably one I'll do today, another one again I'll repeat it tomorrow, so that this particular case gets into your head. So this is the case of weak coupling and beat. So first case, if I just say that, if I say that my x1 corresponding to this, so the displacement corresponding to this is x1, displacement corresponding to this is x2. Okay, and initially let us say that we are x1 was displaced to some extent, let's say small a, and however your x2 was not changed at all. So this is one of the case. Another case can be to keep this particular mass at rest and pull this here. However, I'm saying the answer would come out almost like functional wise, it will be same only. But we'll do both of these cases, and we'll see how you can say x as a function of t would behave and how x2 as a function of t would behave. So this is our initial inquiry with this regards. The only case is that we are taking the case of weak coupling. Okay, weak coupling means what? Weak coupling means that your spring constant here is very less compared to this small k. Is that clear? So that we'll see later on. Okay, so we will initially solve the equations in general, and then we'll see that what you can say that this kappa is very less than small k. Is that clear? So is that clear or not?
Yes, sir. Yes, sir.
Okay. Again, the problem remains the same. Problem remains the same. So let us displace. So initially only this particular mass is displaced by a point like A, but we'll start from the initial case only. So we'll start it from here only. We'll solve the general case at first, and then we'll put the what you can say. We'll put the initial conditions. So we'll take the general case only. So let us solve the general case only, and then we'll put these initial conditions. Let us solve the general case, and then we shall place the initial condition. So let's say what is the general case? Uh, Let us consider that this from the equilibrium position. From the equilibrium position, if x1 is displaced and x2 is displaced, the left mass is displaced by x1 and right mass is displaced by x2. What will happen? I can write that my m x1 double dot will be equals to again minus k x1 plus now instead of k I will have to write kappa here, x2 minus x1, and I will write it as k here. Okay, is that clear? So don't worry about these conditions. We'll use these conditions once we solve the differential equation. We'll pose these initial conditions. Is that clear? Okay. In any case, understand even if it is displaced by a, so the total like total if I from a if I move it to x1, so now it will be a plus x1. So displacement sorry, the spring elongation would remain the x1 only, right? देखो होता क्या है दिस x क्या होता है स्प्रिंग के अंदर जो कि x होता है ना व्हाट इज x x इज द डिस्प्लेसमेंट ओके सो अगर आप कह रहे हैं कि आपका जो दिस मास इज वाज एट a initially and now you displace it by x1, so now total displacement would be a plus x1 minus x1, so again it will sorry minus a, so again it will come as x1 only, so don't worry about it. Is that
यस
clear
सर,
about
दैट्स
it?
क्लियर।
ठीक है so
सर ये इसमें x2 ग्रेटर देन x1 ऐसा कुछ नहीं होगा?
हाँ हाँ बिल्कुल बिल्कुल that I have taken x2 greater than x1, that I will have to take because otherwise there would be no sense. Okay, is that clear? बाकी
यस।
कपलिंग मतलब सीन में नहीं आ पाएगी, है ना? So m x2 double dot would be equals to what if I reiterate the same conditions minus, and I will have to be certainly cautious with regards to the symbol. This is what literature uses, so I'm not experimenting much here. Minus k, and I will array इसको ढंग से कर लेते हैं बेटा इसको. So it will be minus kappa, and then I will write x2 minus x1. Is that clear? So these two are equation. Instead of k, now you have a kappa. So this is the middle spring. So middle spring has a different spring constant given by kappa. Okay, and let us not because here you have only terms in x1 and x2. So you can use the first method also here. So one can use the first method prescribed in the previous lecture. And what was that? That also you can do. You can take a trial solution also. Both of them you can do, but here it is relatively easy to use that, so I'm using that. So I'll just write a sum of the both equation number 1 and 2. So I'll write the sum of both equation 1 and 2. It will be minus omega square x1 plus x2. Okay, so minus omega square x1 plus x2. And what should I do about this? I'll have to use some different symbol for this. So um, if I added these two up now, so if I added these two up, what I will get? There's some mistake or what? So this is plus, this is minus. Okay, so this will go off. This will be 1. Okay, so I'm using omega square for this. Don't forget, otherwise there will be एक बार confusion हो गया, then we'll not be able to recuperate. Okay, and another one would be to subtract equation 2 from 1. So another one would be to subtract equation number 1, equation number 2 from 1. So x1 minus x1 double dot minus x2 double dot will be equals to what should I write? I should write 2 kappa. So I'll write यहाँ ऐसे लिख देते हैं 2, एक बार के लिए तो ऐसे लिख देते हैं 2 kappa upon m, and there's some mistake about sorry, this will be like x2 minus x1. This will be like x2 minus x1. Is that clear? This will be your equation number 2. Is that clear or not clear? Okay. So इसको एक काम करते हैं, इसको ओमेगा स्क्वायर को बाद में संभालते हैं, बिकॉज देखते हैं दो फ्रीक्वेंसीज पर ढंग से लिखने की कोशिश करते हैं. सो मैं तो बहुत सारी चीजें हो जाएगी, एक मिनट को इसको बाद में देखते हैं. एक बार इसको ऐसे लिखने की कोशिश करते हैं, सो दैट यू इसको एक बार के बाय एम लिखते हैं, थिंग्स विल रिमेन इजी फॉर अस. क्या चाहिए इसको? Okay, so just give me a minute. इसको एक काम करते हैं. For our conveniences, let us first write it as, that is what I say. Let us first write it as k upon m. Take on this. Okay, so now you can see that there are two independent modes given by x1 plus, like two independent normal coordinates. x1 plus x2 is one of them, which is oscillating with frequency k upon m का root over, and this is oscillating with the frequency. इसमें भी एक एक्स्ट्रा टर्म आना चाहिए मेरे हिसाब से. ये तो हो गया प्लस कप्पा, और इधर से क्या आएगा, माइनस करेंगे तो प्लस के अपॉन एम एंड x2 माइनस x1. ये भी तो आएगा टर्म, है ना, ये भी तो आएगा, बिकॉज ठीक है. सो दिस विल बी एग्जीक्यूटिंग ऑसिलेशंस विद, बिकॉज अगर तुम इसको, चलो इसको सॉल्व कर लेते हैं. सो इसको ऐसे लिखें, x1 डबल डॉट माइनस x2 डबल डॉट would be equals to what? Would be equals to minus of k, अरे यार इसको ऐसे लिखते हैं, small k upon m plus 2 kappa upon m, and then this will be x1 minus x2. Is that clear? So this is another normal coordinate. So one of the normal coordinate is x1 plus x2. This normal coordinate is oscillating, or you can say executing oscillations with frequency root over k upon m. Again, I've written mistakes and write k here in this fashion. And the other one, other normal coordinate is simply x1 minus x2, which is again oscillating with a pure frequency given by root over k upon m plus 2 kappa upon m. Is that clear? Is that clear?
सर x2 माइनस x, सेकेंड इक्वेशन में x2 माइनस x1 कॉमन लेके हम सीधे k बाय m लिख सकते हैं ना?
हाँ, वही लिखा बेटा हमने. सेकेंड इक्वेशन में x1 माइनस x2 लिखा हमने, और एक नेगेटिव कॉमन लिया, तो दिस विल बी स्मॉल k बाय m प्लस 2 कप्पा अपॉन m. ये k अपॉन m नहीं है, तो अंडरस्टैंड दिस पार्ट.
ओके 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 ओके.
यही दिक्कत होगी, इसलिए वो कप्पा, इसका कोई और मैं सिंबल ले लेता, k नॉट इज नॉट अ गुड सिंबल. सो ऐसा कर लिया हमने, ठीक है. लेट अस नाउ फॉर कन्वीनियंस राइट दिस एज ओमेगा, व्हिच वी वर ट्राइंग टू राइट, एंड राइट दिस एंटायर थिंग as some other one, let's say omega dash or omega tilde. Okay, so I'll write it as omega tilde. Done? Is that clear? So you can see that there
Yes,
are
sir.
two independent modes, or you can say modes of frequency modes, or you can say these two independent normal coordinates are executing oscillations with omega and omega tilde. You can understand that individually x1 consists of both of them. So individually if you try to find x1 as a function of t, which we are going to do in the coming, now we are going to do, because now we have additionally initial conditions given to us, so at least we'll be able to find things to some level. And you can see that x1 would be function of, will contain both omega and omega bar, like omega tilde, and x2 will also contain both omega and omega tilde. But x1 plus x2 is executing oscillations with one pure frequency. This is what you call as your normal coordinate. I will insist that you can read your like any book on oscillation waves in the first year also. There you will get a proper definition, but this is what is a mathematical definition. Okay, if I have a independent coordinate which is executing oscillations with respect to a pure frequency, this is called as your normal coordinate, and this is called as your normal mode of oscillations. One of the normal mode of oscillation has a frequency, or you can say one of the normal mode is corresponding to frequency omega, which is root over k by m. Another normal mode of oscillation has a frequency omega tilde, which is root over k by m plus 2 kappa upon m. And that is why I was not using this because, okay, are you getting my point now? Till now? Now, let us use the initial conditions given to us. So, initial condition was imposed, and let us impose some initial condition on the speeds also. So, let us keep them. Let us impose initial condition that they are released from rest. Impose initial condition that they are initial conditions that both of them are released from rest. So that implies your x1 dot will be 0. Your x2 dot at t equal to 0 would also be 0. Is that clear? So both of them are released from rest only. The only point is difference is that x1 is has some sort of initial displacement given at initial times, and x2 is at rest, and also it has not been displaced. So initially some displacement has already been given to x1. So this is how it is. Okay. Is that clear? So equilibrium position to x1 initially was given as a, and x2 was 0 only. And then from a we have, so now we are going to use these two conditions in order to obtain x1 as a function of time and x2 as a function of time. Is that clear? So we've obtained that x1 plus x2 would be some constant. Let us write it as a cos omega t, and let us write some initial constant. इसको क्या बोल देते हैं? Let's say 5 बोल देते हैं. And this will be x1 minus x2 will be some b cos omega tilde t plus 5 tilde. Okay, is that clear? Now, if I want to extract my x1, so x1 as a function of time would be simply what I can write x1 or एक काम करते हैं. Now let us try to impose the condition. So let us now try to impose the condition. First condition is x1, both the conditions, x1 equal to 0, x1 dot equal to 0, x2 at 0 equal to 0, and then you have this x2 dot at 0 equal to 0. Okay, so now you use these two conditions. What you'll get simply so I'll write it here. So what I will get, so at t equal to 0, x1 was 0, x2 was 0, so I'll replace 0 here, so I'll get a cos phi.
T equal to 0, x1 is a, no?
हाँ बेटा, अच्छा, x1 at 0 was given as a, sorry. So I'll write a cos phi as simply small a, right? And if I differentiate the above, I'll get x1 dot 0 will be 0, x2 dot will be 0, and I'll get minus omega a sine phi as 0. Is that clear? Which will give me that my omega must be some n pi. And let us take that initial phase to be 0 for simplicity, because there are like many solutions to it, but let us take phi to be 0, one of them. Okay, so let us get rid of this phi. So if I get rid of this phi, so I'll get capital A is equal to small a. And similarly, in the second case, if I impose these conditions, what I'll get, I will simply get, because the same structure is there, if I differentiate it with respect to time, I'll get x1 dot minus x2 dot is equal to minus omega tilde b sine omega tilde plus 5. And if I replace at t equal to 0, x1 dot equal to 0 and x2 dot equal to 0, I will obtain that my phi tilde would be 0. And if my phi tilde is 0, what I'll obtain that this is 0. And if I replace at t equal to 0, my x1 was a and this was b. So I'll obtain that my b is also equal to small a. Is that clear? I hope this is clear to you. And if I get both of these things in place, so what I'll simply get that x1 would be equals to a upon 2, because this, if I add both of them, cos omega t plus again a upon 2 cos omega tilde t. And also if I replace x2 as a function of time, so x1 as a function of time, I have this, and x2 as a function of time, I'll again get a by 2 cos omega t, and then I will get a by 2 cos omega, sorry, minus होगा ना, x2 को निकालने के लिए minus करना पड़ेगा. Is that clear? And if you've not forgotten the formula of cos c plus d is what you can say, cos c plus d by 2 and cos c minus d by 2. And if I replace cos c minus, if I write cos c minus cos d, that would be sin c plus d by 2 and sin c minus d by 2. Is that clear? And
सर
what is, हाँ जी बोलो.
सर एक डाउट है, ये जो सेकंड कंडीशन हमने डेरिवेटिव वाली ली है,
हाँ,
उससे हमने क्या निकाला?
देखो, पहली कंडीशन आपने ली एट टी, पहली कंडीशन आप लो एट टी इक्वल टू 0, x1 was a and x2 was 0. सेकंड
यस
कंडीशन
सर.
में हमने ये कहा कि मान लेते हैं कि दोनों रेस्ट से स्टार्ट होंगे. रेस्ट से स्टार्ट होने का मतलब तो इनिशियल वेलोसिटी टू बोथ ऑफ दीज इज 0. सो इफ x1
यस
dot
सर.
is 0 at t equal to 0 and x2 dot is 0 at t equal to 0, differentiated. So what you'll get, 0
यस सर.
plus 0, and you'll get
यस सर.
minus omega a, okay, and then you will get sine
विल गेट साइन
omega
ओमेगा टर्म विल आल्सो बी देयर ना. ओके सर, ओके.
t plus
आपने
I
नीचे सिर्फ फाइव लिखी थी इसलिए.
equal to 0. ठीक है, and this is at t equal to 0, so forget about this. From here you will get sine phi equal to 0, which will mean that phi should be equal to n pi. Okay,
ओके
and
सर.
for simplicity I'm taking, let's say, omega equal to 0. So not let us not add some phase to it, let us start from phi equal to 0. So is that clear to you?
यस सर.
Is there any issue till now?
सर मतलब डाउट ये था कि हम t इज इक्वल टू 0 पे कंडीशन निकाल रहे हैं डेरिवेटिव की, लेकिन हम सोल्यूशन लिख रहे हैं वो कॉमन x1 t पे लिख रहे हैं, जनरल t पे. तो जनरल t पे जो डेरिवेटिव रहेगा वो डिफरेंट रहेगा ना सर?
uh, I didn't get your point. देखो, uh, यही तो है. देखो अगर थोड़ा ध्यान से देखोगे, so x1 as a function of time plus x2 as a function of time is given by a cos omega t plus phi. Is that clear?
वो इनिशियल कंडीशन में कहते फाइव के लिए हम लगा रहे हैं क्या, वो फाइव इक्वल टू 0 करने के लिए x1 डॉट ऑफ 0?
एक मिनट वापस बोलो, सॉरी मेरे को समझ नहीं क्या कह रहे हो.
हम्म.
At t equal to 0, we know that x1 at t equal to 0 is a and x2 is 0, so this will be like a plus 0, and here I'll get a and I'll get cos of phi. Is that clear? And if I differentiate it, so if I differentiate, I'll get x1 dash at t plus x2 dash at t is equal to minus omega a, and then I'll get sine omega t plus phi. Is that clear? Now, if you replace at t equal to 0, your x1 dash was 0 and your x2 dash was 0, so this is 0, and this will be minus omega sine phi. This is what I'm telling you right now. I don't know where's
यस
the.
सर.
चलो
हाँ.
देखते हैं. Let us see. Well, I don't know what is going wrong. I mean, at t equal to 0, in any case, this particular thing will remain sine phi only, and this will become 0. So this is 0, so that implies sine phi would be 0, and that implies the choices for phi are limited to n pi, and let us take phi equal to 0 for that matter.
ओके सर.
Okay, so this is how your function would look like for x1 and x2. And there is a tradition, because lately you will see that there will be an envelope to the, like the solution would look like as if there is a main wave modulated by, like there would be a, I'll explain you all those things, but there is a certain notation that usually is taken. So in many books you'll find it as omega f, that is omega fast, and omega s, that is omega slow. But we'll keep things simple. I'll write omega is equal to omega plus what should I say, omega bar divided by 2, and minus, again I will write omega bar minus omega divided by 2. Okay, this is one. And another one would be omega would be equals to omega bar, I can write as omega bar plus omega divided by 2, and then I can write plus omega bar minus omega divided by 2. So this is how we write. This is one of the things, this is how you can write things. Okay, is that clear? I mean, this is you'll see what sort of implication we'll get from here. Okay, so this is what we'll do. Okay, now if I use them up, so if I use them up, instead of omega, if I write this omega plus omega bar divided by 2 minus omega bar minus omega upon 2. Why I'm doing this? Because I know that cos c plus cos d is what? So cos c plus cos d is 2 cos c plus d by 2 and cos c minus d by 2. So I'll write cos c plus d by 2 and cos c minus d by 2. Is that clear? And similarly, x2 as a function of time, I can write it as a sine c plus d by 2 and then sine d minus c by 2. Is that clear? Or not clear? ये चीज समझ में आई, ऊपर से चली गई, इसमें तो कुछ है ही नहीं.
Yes, sir. Yes, sir.
Okay. And understand that uh, if I want, what is my omega? So my omega was, oh sorry, omega tilde was what? So let me write my omega tilde at first. So what is my omega tilde? So omega tilde was, I think, the natural frequency of oscillation plus 2 kappa upon m. And now let us consider the case. Let us consider the case of weak coupling. Let us consider the case of weak coupling. So if this is weakly coupled, what does it imply? It implies that the spring constant of the second spring, like middle spring, is very, very less than the other couplings, like spring constants. Is that clear? So what I'll do, I'll simply take, instead of omega, I'll write it as, I think we like this, small k upon m. So if I take this root over small k upon m, what I'll get? I'll simply get root over 1 plus, there would be some 2 kappa upon k. Is that clear? And
Yes.
what we do, we actually take this, what I do is actually take this linear, I'll expand it binomially. So this will be like root over k upon m. Okay. And then I will write it as plus 1 plus, and this will be like kappa upon small k. Like 1 plus nx, 1 plus x is 1 plus nx. If this is very, very small. Is that clear? And usually what is done, this particular term is written as some very small number, let's say 2 epsilon. Is that clear? And this
Yes, sir.
particular term, we know this is omega. So I'll write it as omega plus 2 epsilon. Is that clear? Yeah, like root over k upon m into this, I'll write it as 2 epsilon for some so for some simplistic reason, because if I use omega tilde as omega plus 2 epsilon, so this will be in symmetry here. So at least I'll get 2 epsilon, like 2 epsilon upon 2, so I'll get epsilon here. Is that clear? So there is no other reason, because epsilon is small, then 2 epsilon is also small, just to keep the symmetry intact. There's no other way. If you can also use epsilon here, but then you'll have to keep this epsilon by 2 epsilon everywhere. Okay, so we are considering the case of weak coupling, where the middle spring is having a lesser spring constant than the other two ones, like other two springs. Is that clear? And omega tilde I'm getting as omega plus 2 epsilon, where 2 epsilon is kappa upon small k. Okay, so I'll write it here. So your epsilon here is, so that you'll remember. So epsilon here is nothing, but it is equal to kappa upon 2 epsilon, 2k, and then there will be some omega also. Okay, is that clear? And omega is what? Omega is your root over k prime. So your this is kappa, kappa upon, I'll write 2, and this will be like small k, and this will be like root over k prime. Is that clear or not clear? ये चीज समझ में आ रही है कि बिल्कुल ही ऊपर से जा रही है? Okay, and if you multiply with root m both of the sides, so this will give you kappa actually थोड़ा सा तो मेरा पेन भी slow चल रहा है, कोई बात नहीं, पर we'll see. So this will be like kappa upon 2m, and then there would be some term like is that clear? So this is your epsilon, nothing else. Okay, but what it will do, it will in this certain in this particular approximation, your approximated solutions to the displacement would become this. So x1 as a function of time would become a what it was equal to cos omega plus omega bar. So this will be like cos omega plus omega bar. So this will be cos omega plus 2 epsilon. So this will give you omega plus epsilon t, and then other term would be cos epsilon t. And x2 as a function of time will give you a sine omega plus epsilon t, and then you have sine epsilon t. Is that clear? ये चीज समझ में आ गई, इसमें कुछ बड़ी बात नहीं है, सिंपल रिप्लेसमेंट्स है. So we already know that we are talking of weak coupling. So your kappa would be less than k, and this is epsilon in that case would be very, very, very less than omega also. Is that clear or not? Is that clear or not?
Yes, sir.
Okay, okay, thank you. Chalo. So in this particular limit, what I can say that if this is very, very small, so this omega is very small as compared to this. So what I can say, this component, like this component would be, will obviously be contributing to oscillations, but it will be oscillating like you can say at a slower pace than this. Are you getting my point? Because here, if epsilon is very, very less than omega, this term like can be written like omega t only. This can be written like omega t only, right? Okay, so this is like omega t only, and this is very, very small. Like this will be as if it is a constant, because see epsilon, if it is tending to 0, cos 0 is almost equivalent to 1, or not even that. If you say with respect to this particular frequency, this particular oscillation would not be that great. Is that clear? I taught you in the very first day that if I plot the graph of sine, this is it. If I plot the graph of sine 2, this will be it. So, and if I plot the graph of sine 4, so this will be like this. So are you getting my point? So if this is very like this epsilon is very less, so this oscillation would go at a very slower pace than this cos of omega plus epsilon t. Is that clear?
Yes, sir.
Okay. So what should I write? I write that this term would oscillate at a slower pace. I'm not getting the right word, but at a slower pace than the first term. So this particular thing would oscillate slower oscillations than this one. And in fact, you will see that because epsilon is very, very less, so I can say that it is almost oscillating with omega only. It is almost oscillating with omega only. So are you getting my point? So it is almost oscillating with omega, and this particular epsilon t is very small. Like this is very small as compared to this. So what you can say that this x1 as a function of time is nothing but a cos epsilon t, and then you have this cos omega plus epsilon t. Like physics, mathematics wise solution is over. This is what your exam would ask. I'm just trying to make you feel this. And today I was seeing in the morning there are many simulations available, so you can see those also on internet in order to better comprehend it. So as much as I understand, so this will be like an envelope to this. So this is like an envelope to this. जनरली क्या होता है, यहाँ पे कांस्टेंट a होता है. So आपका क्या होता है, your function like if it is a cos theta, so it will be like this only. Now instead of this, your envelope is again a cosine function, which is again changing as a function of time. Is that clear?
Yes, sir.
Okay, so basically what is happening, this x1t is almost oscillating with this dominating frequency omega, because this epsilon is not going to matter much. So I'll write that my x1 oscillates with almost frequency omega with an envelope this. This is envelope which is again a time dependent envelope with a time dependent amplitude. So it is oscillating with a time dependent amplitude. In fact, time dependent sinusoidal amplitude. Like sine and cosine are by only, hardly a difference of pi by 2, like phase difference by 2. Okay, is that clear to you? So tentatively, what you can say that there would be a, what you in the theory of modulation, this is said as, if I make this, so this is your, uh, so this is how your cos behaves. This is how your cos behaves. Okay, and if this is your main epsilon one, so I'll write it as cos epsilon t. So as I explained, if I write sine, this will be like bigger one, like this one. And if I write cosine, sorry, sine 2, so this will be like rapidly oscillations. And if I'm saying that as compared to epsilon, your omega is very, very large, what will happen? Your cos, this particular envelope, so this particular x as a function of t would uh, would take values from here to here. So the amplitude will take the values from a cos epsilon t to minus a cos epsilon t. So this is a cos epsilon t and this will be minus a cos epsilon t. So this will form an envelope. Okay, so this will form an envelope in which your x1t is dominantly executing oscillations with frequency omega. So what is going to happen? This particular thing will start oscillating in a manner only of cosine only. Is that clear or not clear?
This blue one is omega plus epsilon, right?
हाँ बेटा, ये जो blue one is your omega plus epsilon. Is that clear or not clear?
Yes, sir.
Okay, and also understand that this will be your envelope, that is cos epsilon t would be envelope, and sorry ये लिख देता हूँ मैं यहाँ पे तो confusion होगा. This will be like cos omega plus epsilon t. Is that clear? So initially your amplitude was a, and at some point this point कौन सा होगा जहाँ cos pi by 2 होता है, तो मतलब ये time कौन सा होगा, time हो जाएगा where your epsilon t would be pi by 2. Is that clear?
Yes, sir.
Incidentally, you will see that at this time your x2 will achieve maximum because sine at pi by 2 is maximum, cos at pi by 2 is minimum, but sine is maximum. Is that clear? So at this time
Yes.
your x1 is transferring energy to x2. So basically your another mass is in motion while your first mass is at 0. Like उसको भी बना ही देते ना. The second case क्या होगा? Second case में क्या है? Second case में your envelope will be a sin epsilon t. मैं यहाँ बनाता हूँ. Second case में your envelope will be a sin epsilon t. यही होगा. And because like sine is a sinusoidal function lies between -1 and 1, so envelope will be like this way. फिर इसको मेरे को सही बनाना था यार, गलती कर दी. रुक जाओ थोड़ा सा ऐसा, कोई बात नहीं. रुक जाओ. ठीक है. सो व्हाट आई वांटेड टू मेक वाज, एक मिनट अपने पास समय भी कम है, कोई बात नहीं, इसको कल कंटिन्यू कर लेंगे, बट एक बार इसका ग्राफ बन जाए. ठीक है. सो दिस इज व्हाट आई वांट टू एक्सप्लेन. ठीक है. सो यहाँ से चालू किया ना, इसको यहाँ से चालू करते हैं, एग्जैक्टली यहीं पे खत्म करते हैं. ठीक है. जब ये मैक्सिमम होगा तो हमारा साइन मिनिमम होगा. इज दैट क्लियर? और जब ये वापस से मिनिमम होगा तो हमारा साइन वापस से मैक्सिमम होगा. जब हमारा कॉस मैक्सिमम होता है तो हमारा साइन मिनिमम होता है, सो एंड सो. इज दैट क्लियर नॉट? सो होगा क्या, दिस इज योर सेकंड केस, दिस इज योर x1 एंड दिस इज योर x2. ओके.
सर
एंड
pi by
नाउ
2 पे तो आपने 0 कर दिया.
x2 is maximum. This is getting stuck also, I cannot help it.
सर ऊपर वाले ग्राफ में ही डिफरेंट
मतलब
कलर से
ऐसा
ड्रॉ कर
करेंगे तो
सकते
समझ नहीं आएगा यार, एक्चुअली today's
हैं अलग कलर से।
has been changed now, so it is giving me difficult time. चलो कोई ना, I'll take another 15 minutes of yours and we'll continue it in the next lecture because hardly 1 minute is left. Okay, so try to make this graph on your own, and we'll take it either today or tomorrow. We'll take it tomorrow only. So if I make this graph here, let's start it from here. Here it will be